Shall we? All right. So now we're going to switch to talking about. So just to recap quickly. So we talked about the amplitudes. The example I actually talked about reading the amplitudes at tree level. The diagrams have the loops in them. We have the very simplest amplitudes for this theory of colored particles, the trace phi cube theory. And just to summarize, we just talked about what the kinematic space was. So what's the actual variables? What are the kinematic variables that the amplitude depends on? It's an especially nice way of thinking about them. In terms of the momentum polygon, we can abstract away the chord distances as just the variables the amplitude depends on. The amplitude could be written as a sum over triangulations of a polygon. All of the drama is about non-crossing chords. Okay, so we're only allowed to have diagrams where chords don't cross each other. If we drew things where chords cross each other, then there is no dual diagram that we can associate with it. That exactly says there is no space-time process we can possibly associate with a picture that has chords crossing each other. And so we just talked about what locality and unitarity mean for this amplitude, that there are simple poles, and on the poles, the corresponding to some chord, the amplitude just literally factors. The residue on the pole literally factors into the product of the amplitudes you associate with inclined surfaces. So to say again, the entire point of what we're trying to do is to go back to this kinematic space and find another question that we can ask directly in the space of these x's that will give rise to a function that has all these properties, right? Without putting in that we have imagined that there are particles, Feynman diagrams, and so on, right? The entire point of this adventure is to find some set of ideas from which locality and unitarity are the output, not being put in by hand as the input. Okay, that's the whole point of what we're trying to do. But what we've done so far is just set ourselves up for success. Okay, we've talked about what the kinematic space is, talked about what the properties are that have to be satisfied, and then we'll come back and talk about what the objects are that are going to do. Okay, but I want to keep going with kinematics now and talk about cosmology. Now, the kind of observables we talk about in cosmology could not, on the face of it, look more different than scattering amplitudes. Scattering processes are experimental physics. You get to control the initial state, apply some things, some final state comes out that you can measure. Okay? So it's very active. It's an experiment. It's not an observation. Okay? In cosmology, they're observables. They're not experiments. We do observations of cosmology. This is for many reasons. One, there's one universe. Two, none of us were around in the early history of the universe, right? None of us were there. Cosmology is just the most glorious of the historical sciences. And like any historical endeavor, be it cosmology or paleontology or being a detective, your job is to infer the existence of some history to explain some pattern of correlations that you see in space in the present. Okay? So a paleontologist says that a big dinosaur existed that ate a little dinosaur, not because they were around back then to see the dinosaurs eating each other, but because they see in the dirt today a bunch of bones that seem like big teeth with a bunch of other little bones inside it that look like smaller things that were eaten by the big thing, right? So that's a pattern in space that you infer the existence of a history to give a rational explanation for. Or a detective says that person A murdered person B because a bullet from a gun belonging to person B was found in the body of person A today. They weren't around yesterday to see the murder happen, but they have a theory for the existence of a history in order to give rise to an explanation of the correlations you see in the present. Exactly the same thing is true in cosmology. For example, the only observations we can do is sit on our back and look at the night sky and say, what fraction of stars are red, what fraction are blue? Right? That's one kind of question. Or you can ask how much hydrogen is there versus how much helium is there versus other things, right? So those are things that you could call one-point functions, right? They look just in one region of space and they talk about one quantity in one region of space. Beyond that, you can start correlating what things look like from 2-point, 3-point, higher point functions. Now, there's a beautiful picture. I mean, this is not a physics talk, but I can't not tell you this. There's a spectacular picture, maybe one of the most spectacular stories that we have in all of physics, for where all of the structure that we see in the universe around us came from. Okay? So you all know that the universe is expanding. There's colloquially some kind of Big Bang where the curvatures became infinite and so on. But for the past 30 years, we've had more and more evidence of a picture in between the Big Bang and what we have now, where the universe underwent a period of so-called inflation. And that's where there was a period where the universe grew in size exponentially, so doubled in size at a uniform rate. Now, what this exponential growth allows, which any sub-exponential growth does not, but what the exponential growth allows is the following amazing thing. You have, at least intuitively, a picture of quantum mechanical fluctuations in the vacuum. But the idea is that things are fluctuating back and forth, waving up and down, up and down, up and down, but then mostly they average out, so you don't notice them. However, if the universe is expanding exponentially, then those little fluctuations just don't have a chance to cancel out. They're being stretched more quickly than they have a chance to cancel out. And so those tiny quantum mechanical fluctuations during this period of inflation are stretched out to enormous distances, and they turn into regions in the sky that are a little bit hotter, have a little bit more energy or a little bit less energy. The regions that are a little bit hotter end up having a little bit more matter in them than the colder regions. The regions that have a little bit more matter then by gravity will collapse under their own weight, and that's where the galaxies will form. So the origin of all structure in the universe in this picture is tiny quantum mechanical fluctuations very early on that are spread out by inflation to turn into all the structure eventually that we'll see in the world around us. Okay, so the origin of all structure is these tiny quantum mechanical fluctuations, and we have experimental evidence for these fluctuations just by looking at the temperature of the cosmic microwave background. So you probably all know one of the basic evidences for the Big Bang theory is that there's this roughly 3 degrees Kelvin temperature in every direction you look. But in the early 90s, it was discovered that the temperature is not quite the same in different spots in the sky. And there's roughly a 1 part in 100,000 difference between the temperature here and there. Okay? So there is hotter spots, colder spots. They differ roughly by 1 part in one part in 100,000. And so if you look at this sort of variation of the temperature, delta T over T, at some angle, theta 1 on the sky, delta T over T, angle theta 2 on the sky, you can look at what this 2-point function is. What does that 2-point function mean? So let me put a point here and another point at some fixed normal vector relative to that one. What this means is that you literally look at what is here and you choose the angle, the part that you wanted there. You multiply the delta T over T here times there, and then you just average over all the points in the sky with that separation fixed. Okay? So those are the kind of observations that are experimental. They're observations, they're not experiments. They're the observations of the night sky, of the temperature that you can do. Of course, it's just by definition, the expectation value of delta T over T itself is 0, just by definition, that we take out the overall mean temperature. But already these 2-point functions are consistent with totally Gaussian noise, right? There's Gaussian noise. This is something of order 10 to the minus 5 squared. And that's, again, consistent with the idea that delta T over T is around 1 part in a 100,000. Okay, so these are what you can call 2-point functions. These 2-point functions, which we can just measure from hotter and colder spots in the sky, are really a measure of quantum mechanical fluctuations of the particles that were present during inflation. So again, it's not a physics talk. I won't give you more of an explanation than that, but this is, I think, all we'll need for understanding what the kinematics are. I want to make an important point. I told you that these are quantum mechanical effects. And so I'm sure you all know that the quantum mechanics doesn't allow you to predict anything with certainty. You can only predict probabilities. So it's important to say, what probabilities are these? Okay? Normally, when you talk about quantum mechanics in the textbook, you say you do the experiment over and over again, and it's like flipping a coin. That's what when you say it's a fair coin, it means if you flip the coin a million times, you should expect to get heads or tails plus or minus about 1,000. But the usual square root of n size fluctuations. But in order to get the precise predictions, you have to repeat the experiment over and over and over again. What experiment is being repeated over and over and over again here? Nothing. We had one universe. But the experiment that's effectively being repeated over and over again is the universe is very large, and the different regions in the universe are sort of operating on physics rightfully independent of each other. So the averaging we're doing is not over trials, is over space. Okay, so that's why we can't just predict what is delta T over T at this spot times that spot. That's random. But if we average over all the spots with a fixed separation, that's something which is a prediction of a quantum mechanical theory. And it's a prediction of these underlying quantum fluctuations during inflation. So, so 1-point functions is almost everything people have fun with in astronomy and cosmology. How many red stars, how many blue stars, how much hydrogen, how much helium. 2-point functions have been measured to death over the last 30 years by measurements of the cosmic microwave background and relatives thereof. And people are desperately looking experimentally, observationally, for the evidence for 3-point functions. And because a 3-point function would tell you that it's not exactly Gaussian, right? There's some small correlations between all of these fluctuations. And we should expect that there are small fluctuations between all these correlations because there are interactions everywhere in nature. Everything interacts with gravity minimally. And there's other more interesting interactions that we might imagine happening besides. So we should expect that there are higher point correlations. And one of the reasons it would be very exciting if this was discovered in experiments is that the energy scales involved in this early inflationary period are like easily 10 or more orders of magnitude higher than any energies we can achieve on Earth in accelerators. So if we could notice the effect of small non-Gaussianities, small 3-point functions, 4-point functions, then that would indirectly be giving us access to a physics and energies we could never hope to probe on the planet, never mind in the galaxy, very, very likely, with accelerators even the size of the galaxy. Okay, so that's all motivation. But in the end, what is the measurement? When all is said and done, the measurement is I have any quantity, for example, this delta T over T. And let me imagine that I could actually measure it not just on angles of the night sky, but really as a function of distance away from me. So full 3-dimensional points. So I have some x1, delta T over T as a function of x2, and so on. And again, what I mean by this is that I plot down my x's and I just translate all of them. I integrate over the configuration with the relative x's held fixed, and I average over all space. Okay, so these are the observables that we're talking about. Because of translational invariance, as usual, it's useful to represent these things in Fourier space. Okay, whenever you have translational invariance, it's useful to represent these things in Fourier space. So from these things, we can get functions that are called cosmological correlators. So cosmological correlator, which depends on some K1, K2, Kn, right? Except, of course, this is also always going to be on the support of momentum conservation because of translational invariance. Okay. All right. Now, I've emphasized this for the actual cosmology of our world. So I literally mean, imagine we could do this measurement. We haven't done it for already n equals 3 is a waving being done. Okay, but we can imagine by observation, but we can imagine doing it. There is another setting in which we could do exactly the same thing. It has nothing per se to do with cosmology. So something else that you can do is take any state of matter at all and ping it in exactly this way. You can ask for sort of you could measure any quantity that depends. You see, what's important about this is that it doesn't depend on time. The measurement is being done now. Okay, and so any measurement of some correlation which is done at a fixed time is going to have the same property. Okay? So it doesn't have anything per se to do with cosmology. It's any measurement of any quantum mechanical quantity that's done at a fixed time is going to have the same basic kinematic features. I'll come back to this point in a moment. Okay, so now let us imagine that the theory that we're talking about is again this trace phi cube theory, so that we have a natural ordering. Again, we have a natural ordering. Okay? So just to give you a picture, I might draw this picture a number of times. So here's a picture of space and time. This is space. Okay? Here's time. So here's now. This is the past. And so the picture that I mentioned is that, okay, there's some period down here called inflation. And it's driven by scalar fields. And so you would draw sort of Feynman diagrams in order to compute the observables. The observable all takes place here at t now equals 0. Okay, so everything is taking place here. But you know, there was some time dependence here. Something happened. Some quantum mechanical perturbation was born. And so it would correspond to a very simple Feynman diagram that depends on the two anchors here. Maybe there's point x1 and x2. Okay. This is what we've actually measured today, right? That's this 2-point function that I've told you about. But there could be corrections to it. You know, maybe I could look at a 3-point function. Okay, so that could come from a diagram that looked like that. I could have a 4-point function. That could come from diagrams that look like this. They look exactly like the same kind of Feynman diagrams we always draw, with the one important difference is that everything is anchored to this late time surface where the measurement is being done. All right, that's it. That's the only difference. And so if we imagine that what we had in the interior was trace phi cube theory, then I would draw exactly the diagrams that we had before. Nothing has changed. Again, the only difference is we imagine that all the legs are anchored to this surface at AD equals 0. Okay, so I'm trying to give you the minimum amount of knowledge you need in order to see at least what the difference is in the kinematics between between the case of amplitudes and the case of cosmological correlators. Okay, so what is the kinematic space here then? So what is the kinematic space? The kinematic space is just a bunch of spatial momenta, k1, k2 up to kn, with the sum of the k's equals 0. That's it. Let's contrast this with the amplitudes, where I have P1, Pn, where the sum of Pi equals 0. What's the difference? The difference is just that there's no 0 component. There's no energy, right? That makes sense. I mean, it's a static measurement, right? It's a okay. All right, but remember that Pi was Ei and Ki. Okay. Also remember that Ei squared was not random. Like Ei squared is equal to Ki squared plus m squared. Okay. So in fact, the kinematics for these two problems are almost identical. That's what's hysterical, right? That the physics looks as dramatically different as could be. One of them is a super active, I collide things from infinity, boom, they go back out. The other one is I sit there like a lame duck looking at the night sky, correlating some things, right? They look as different from each other as possible, and yet the kinematics is almost identical. In fact, both cases are associated with a picture of a polygon, right? Because if I looked at just the spatial component, in both cases, I get a closed polygon. So In both cases, there was a closed polygon, K1, K2, up to Kn. It's just, this is all there is. This is all there is for the cosmological correlator. Whereas for the amplitudes, I also have that the sum of EI is equal to 0, where the EI are plus or minus root KI squared plus M squared. Okay, so this is cosmology, and this is amplitudes. Okay. Now, if these were purely physics lectures, I would now tell you how to derive these cosmological correlators from the ground up. But since they're not, if people are interested, I'm very happy to give a little mini lecture about it at some point today. But let me tell you, just like I told you, what the answer ends up being for the amplitude in terms of sums over triangulations, I'm going to tell you what the answer ends up being for what's called the cosmological wave function. And actually, I'm going to do something else. First, I'll call it the flat space wave function that depends on these variables. Never mind what that flat space wave function means. I might explain it in a second. But there's some small steps from this object to the actual literal cosmological wave function. If what you had in this inflationary period was trace phi cube theory, in that early in inflationary era, okay, what's called conformally coupled trace phi cube theory. But what I'm about to tell you is I think going to be enough for you to get the idea. Okay, so now it's just a function of the k's, right? So I'm going to tell you what the rules are. And I'm first going to tell you what the rules are for a single diagram. Remember that if we had an amplitude, we have this. Then here, I was supposed to just write down 1 over P1 plus P2 squared. Right? That's the propagator. And this is 1 over E1 plus E2 squared minus K1 plus K2 squared. Okay, so that was the rule. I'm ignoring the coupling concepts here. Okay, so one diagram, one term. Very simple. Okay, things get a lot more interesting in cosmology because, as we'll see, one diagram by itself is going to be associated with many terms, the sum of many, many terms. But let me actually start with the simplest example of the same diagram, the cosmological analog of the same diagram that still ends up being one term. All right, so let me tell you how to think of what the expression ends up being. So I'm skipping a 45-minute derivation. Okay? But it's really a 45-minute derivation from nothing, from really nothing. Okay? So it's not hard at all, really at all, but you'll just have to believe me now. Okay, so let's take this diagram. But drawing the same diagram, see, I'm drawing it the same way. This is 1, 2, and 3, 4. Okay, and then now what are my variables? The variables are just this, right? So I have my K1, K2, K3, K4. And even nicely in this picture, you see this intermediate momentum, the spatial momentum is just that one, right? Call that one K intermediate, sum of K1 plus K2, K1 plus K2. Well, let's call that K13, or let me just call it K intermediate. Okay. But here's what I'm supposed to do, to write down the contribution to this object, the flat space wave function, from which I'll get the cosmological correlator in a bit, is I have to take this picture and I have to surround it with little tubes. I have to give what's called the tubing of this picture. So what is a tubing? Well, first I surround everything. Okay. And then it's just every way of circling things that I can, what it sounds like, every way of putting tubes around the picture such that the tubes don't overlap each other. Okay. I'm allowed to have tubes inside tubes, but I'm not allowed to have tubes cross each other. Okay. So this is a tubing of this graph. With every tubing, you write down a factor of the sum of the quote unquote energies that enter the tube. What do I mean by energies? I just mean the magnitudes of the K vectors. So for example, with this big tube on the outside, I would write down 1 over 1, 2, 3, and 4 enter this thing on the outside. So I just write down 1 over K1 plus K2 plus K3 plus K4. Okay. Then with this guy, what do I write down? I write down 1 over K1 plus K2 plus K intermediate. But again, it's just the magnitudes. K1 plus K2 plus K intermediate. And with this one, I write down 1 over K3 plus K4 plus K intermediate. Okay, and so this is the contribution that I get to the flat space wave function as a function of the case from this single diagram. You'll notice that it looks a little bit prettier. Well, I mean, it's quite pretty in both cases, but it looks a little bit easier to interpret here. What is this factor? That's the perimeter of this full polygon. Sum of all the k's. What is this factor, K1 plus K2 plus K intermediate? It's the perimeter of this little triangle. And this guy is the perimeter of this little triangle. So I can also see this as just the product of all the perimeters of the subpolygons that I see in this picture. I have the full polygon and all the subpolygons as well. Okay? Let's do a slightly bigger example. So let's do this one. Then the analog we did before. So 1, 2, 3, 4, 5. Now, does someone want to tell me how to tube this guy? I'll start with the easy tube. It's the big tube. Okay. So let me call this, okay, I'll call this K1, 2. Let me call this 1, 2. Let's say 1, 2, 3. Okay. Does someone want to tell me what to do next?
Why don't you surround the 2 nodes at the bottom, on the left?
These guys?
Yeah.
Okay. I think Professor Williams knows what to do next, but anyone else want to make a suggestion for the next 2? Go ahead, yeah, it's okay. Huh? You want to keep going here? That's good. That's good. Yes. Anything else? You're supposed to keep going. We just plonk down tubes forever, as long as you can. By the way, this is the literal analog of triangulation. It's a maximal collection of non-overlapping tubes. Okay, so the amplitude is a maximal collection of non-overlapping chords. Here we have to write down the maximal collection of non-overlapping tubes. Okay, so what is the next tube? This one. Congratulations. And who's going to get the glorious last tube here? Don't leave it up to me. All right, fine. I'll have the rest. Okay, so this is one. This is one tubing, right? And so this is 1 over. So from here I have K1 plus K2 plus K1, 2. For this guy. From this guy, I have 1 over K1 plus K2 plus K3 plus K1, 2, 3. From this guy, I have 1 over K4 plus K5. From, let's see, shit, how many did I put? 1. Did I miss this one? Oh, I haven't done that. 1 over K1, 2 plus K2, 3 plus K3. And then everything. 1 over K1 plus K2 plus K5. Okay, so that's one contribution to the to this wave function. Okay. Is there another one? Yeah, we can just flip it. In this case, these are only two diagrams. Do exactly the same thing. I can flip it on the other side. So I have two contributions in this case. And let's go back and let's go back and draw this again. So if I think of the triangulation that the underlying diagram corresponded to, again, it was this triangulation. All right, but now let's look again. Just give me a sec. So let's looking at all the terms. What do we have? We have this total perimeter, right? But then well, let's just do the one that we have here. We have this perimeter. See, that's a sub-quadrilateral now, right? And then inside this one, we have this one and that perimeter, and finally this perimeter. Okay. So is it clear what we're doing? Even for a fixed diagram, you take your fixed diagram, but you're not done. It's not just you take the product of all the 1 over x's. That's what the amplitude is. You take a fixed diagram and you sum over all the possible maximal collection of non-overlapping subpolygons that you can associate with that diagram. Okay? That's what we call the Russian doll. Okay? There's a sort of a Russian doll structure because it's like there's the big polygon and there's another one on this side that divides it into pieces. And each one you look inside and there's another one, and you just keep on going until we can get all the way down to the bottom. Okay, so even for a single diagram, it's an interesting object. Okay, it's a sum over all of the maximal collection of non-overlapping subpolygons. Okay. Okay, so I've now given you the rule. So now what is the answer for the? So that's for a single diagram. And so what do I get for the full wave function? It's just the same thing, summed over all possible diagrams. So this full wave function is actually the sum over all maximal collection of non-overlapping subpolygons. Let's call them P, the product of all the 1 over the perimeter of P. So let me call this maximal collection, I don't know, curly P, P inside curly. Okay. Okay, now a couple of comments here. One of them is that remember before we decided that the wave function was a function of the. We decided the wave function was a function of course, it's a function of momentum, but we could write as a function of x's, right? So here we see that the wave function is really naturally a function of the perimeters directly. So it's actually useful to think about the perimeters as just independent variables. Okay? For every polygon, just its own private perimeter P associated. Okay? Now, we don't actually have to do that, and we can go back and forth between a picture of perimeters and the actual Ks. But notice, of course, there's many more perimeters than there are Ks. Okay? There's a huge number of, there's exponentially many polygons at large n. There's polynomially many order n squared K dot Ks. But there's a very nice relationship if you ask for the parameters to satisfy the following. I mean, in other words, if you just abstractly ask for a notion parim associated with any subpolygon to satisfy this property, that is the parameter of P union P prime plus the parameter of P intersect P prime, then of course this is the same as saying that the parameters are parameters. Okay, that they come from sums of lengths that you can associate, okay, with the boundaries. I bring this up because this is the very earliest place we see this basic kind of relationship. So so in the cosmological story, we're going to see these sort of formulas. There'll be various parameters called epsilon, but these sort of formulas, that epsilon p plus epsilon p prime, are either equal or less than or greater than in different settings. Something associated with P union P prime, something associated with P intersect P prime. These are going to be ubiquitous formulae in the entire story, and they're going to be the heart of where all of the action is. Okay, so these are called sometimes submodularity conditions. And if, as I'm going along, everything will seem so sort of trivial and obvious, where's the magic? The magic is in the submodularity conditions. Okay, and we'll see. There's something about. So I'm just flagging this now so that I see this important point earlier. I don't understand why these conditions are so remarkable and so powerful, but they end up having a lot to do with what we're talking about. But just to be clear, if I write this object, it's a formal thing that makes sense for any notion of parim associated with any subpolygon. That's the most natural thing to do from this point of view. If you want to connect it to the actual Ks, then the parameters need to satisfy conditions that look like that. Okay. Okay. All right. Now let me make a final comment. So we've seen that, just one second, we've seen that, so summarizing, amplitudes have everything to do with non-crossing, well, let me call them non-overlapping chords, and this wave function has to do with non-overlapping subpolygons. Already here, those of you who know something about the icosahedron already, which is about half of you, will know the entire story of the icosahedron is about the geometric object, the polytope that captures all the triangulations of an n-gon. So it's all about non-overlapping chords. And the cosmological story is that there's going to be an extension, a generalization of the icosahedron that captures the combinatorics of all possible Russian dolls. Not just triangulations, but all possible, this further richer combinatorial object that keeps track of all possible non-overlapping subpolygons at the same time. Okay, but let me just make a couple of general comments here. So first, this is something I call the flat space wave function. What is this? Well, remember, we're meant to calculate expectation values. So that means that instead of repeating the experiment over and over, we do this average over space, right? But it's whatever we get out of doing this average. In this case, it's an average over all of space. Now, normally in quantum mechanics, like let's say you have a harmonic oscillator in quantum mechanics, and it's in its ground state. Well, we say that the ground state wave function, or the vacuum wave function, the ground state wave function, in the position representation is like e to the minus the half omega x squared. Okay, so it's a nice Gaussian. And if you want to know the expectation value of anything else, you want to know what is the expectation value of x to the 8th, then you're just supposed to integrate over x this ground state wave function mod squared times x to the 8th. Okay, so any old function of x, its expectation value is obtained in this way, right? That's normally the way we calculate expectation values in quantum mechanics. the thing we're talking about is no different. Okay, it's a quantum mechanical fluctuation. It's just that the vacuum was the vacuum in this early universe, in this inflationary era. Okay, and all these Feynman diagrams are just translating the results of that assumed vacuum at early times into what we measure today. Okay, so that's why there's a precise analog of this psi vacuum of X, which in cosmology would be the sort of inflationary, wave functional. So it's not just a wave function of a single X. There's a whole field phi that depends on points X. So it's a whole functional. But this again starts off like a something Gaussian. It's something that goes like phi, some kernel phi, and then it has a piece that's cubic in phi, and quartic in phi, and so on. So this would be just pure Gaussian physics. These pieces include the effects of all interactions. These are the pieces that we calculate from the Feynman diagrams in exactly the way I had told you. Okay, so the calculation of the Feynman diagrams, as I showed you, is on the nose a calculation of this wave function. Okay? Having obtained the wave function, if you want to calculate anything, you do what you always do. You mod square it and you integrate against something. What you want to compute. Okay? And it turns out that these coefficients are extremely close directly to the observables anyway. So if you want the 4-point observed correlation of 4 phi's, it starts off as psi 4 and has some corrections involving psi 3 and so on. Okay? But the sort of beef of it, the most interesting part, is computed by this psi 4 anyway. Okay? But there is a step, there's a second step involved in mod squaring. So loosely, if I want the actual cosmological correlator associated with some K1, K2, blah, 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 Kn, then it would be the integral over all these phi's of this wave function, this inflationary wave function, mod squared, times the corresponding phi's. Okay? This turns out to be extremely simple to compute and very, very close directly to these coefficients. More or less directly built out of these coefficients anyways. So that's why it's a good thing to first restrict your attention to this quantity. Now, this quantity in turn depends on the time dependence of the history of the. It has some dependence on the assumed history of the universe, but it turns out that this guy, this inflationary of K, is some very simple integral simple transform of what I call the flat space wave function, like it is. The flat space wave function is actually what it sounds like. In quantum field theory, in quantum mechanics, we talk about the ground state wave function, like we do in the harmonic oscillator. But we don't normally, in field theory courses, talk about the ground state wave function in quantum field theory. But it completely, perfectly exists, just like any old quantum mechanical system. And so that psi flat is the vacuum wave function. Is a vacuum wave function in just flat space, good old-fashioned flat space. It just turns out that that vacuum wave function in flat space, up to a very simple integral transform, actually gives you the vacuum wave function in any cosmological background, at least for a simple class of theories. Okay, so but if that didn't mean anything to you, it was just so I was saying something completely precise and honest. So bottom line for this class of models, this is the object that contains all the juice. It's the sum over all the Russian dolls associated with all the maximal set of non-overlapping polygons in an n-gon, the product of all the 1 over perimeters. And a suitable simple transform of it would directly give you the cosmological observables that we've been talking about. So that's one comment. Another comment, which is more mathematically very simple to establish, as intuitively, physically very sensible as well, but is still remarkable, is that I have talked about the amplitude And I've talked about the flat space, this flat space wave function. And the remarkable thing is that this amplitude is actually contained inside the flat space wave. Like literally the function is actually inside the flat space wave function. So, let me show you what that means. So let's go back and remember how similar the kinematics were to each other, right? So in both cases, we start with this picture of the momentum n-gon, spatial momentum n-gon. But for the amplitude, we also have the condition that the sum of the energies, which is the sum over the k's with maybe a plus or minus, is equal to 0. Right? That was the only difference, is that we have the sum of the energies equals 0 constraint, which we don't have, which we don't have on this side. Okay. In fact, in the amplitude, there's a delta function for the sum. If I just call these, let me not worry about the sign. Will be implicit in what I mean by the magnitude. There's a delta of the sum of ki in the amplitude, and there's no such delta in the wave function. Okay. However, let's look at our simplest example, where we wrote down. Well, I mean, you see it from the rule. While there's no delta, every single term in this formula has something that's achingly close to the delta function. Every single term, for example, at 4 points, we always have this big tube that surrounds everything. We always have the total perimeter, right? So there's a factor always that looks like 1 over the sum of all the k's, right? So let's look at what it was in this case at 4 points. So here the answer was 1 over k1 plus k2 plus k3 plus k4. And then there's a 1 over k1 plus k2 plus k intermediate, and a 1 over k3 plus k4 plus k intermediate. This is the wave function, and meanwhile the amplitude was 1 over p1 plus p2 squared. They sure don't look the same. Okay? But remember, this is the delta of k1 plus k2 plus k3 plus k4. That's implicitly just the energy conservation. That it's a delta, this has a 1 over. Of course, the k's in a physical region are really lengths here, so they're all positive. But nothing stops us from analytically continuing this formula to imagine that the k's can be plus or minus. Right? So let's say we do that. Let's say we make some of them plus and some of them minus to make this equal to 0. Make the denominator 0. Then the answer is going to have a pole, right? So it's reasonable to ask, what is the residue on that pole? Okay, now you see, it's not going to shock you. The residue on the pole is going to be the amplitude. Okay. Well, first of all, at least it has a chance, because now the kinematics is identical. In both cases, on the pole, I have a momentum polygon with the energies adding up to 0. So at least it has a chance to be the same. But in fact, it is the same. So let's see how it works. So on the supports, let's say I put this to 0. Then that means that k3 plus k4 is negative k1, negative k2. So if I look at what's left, I have 1 over k1 plus k2 plus k intermediate. 1 over k3 plus k4, but that's negative k1 plus k2 plus k intermediate. Well, that's 1 over k intermediate squared minus k1 plus k2 squared. And by golly, that's exactly 1 over p1 plus p2 squared. It's really remarkable. The object wasn't even Lorentz invariant to begin with, right? This is not a Lorentz invariant expression. It's just all spatial vectors, right? Some piece of crap, non-relativistic thing. But on the support of the sum of the energies adding up to 0, miraculously, it turns into the amplitude. Now, there's a very simple reason why this had to happen. And you see, when we normally draw, see here I'm drawing diagrams. I'm going to be a little bit loose here, but this will give you all the intuition you need. I'm drawing diagrams, I'm integrating over all these points. These are some times T1, T2, T3, and so on. Okay. But if I was not doing this calculation where everything here is like anchored at t equals 0, then I'd just be integrating over all times, right? I'd not be ending at the t equals 0. I'd be integrating over all times. Now, when you have a normal, some complicated diagram, when you get an amplitude, where is the delta function for energy conservation coming from? Energy conservation is associated with time translational invariance, right? And so that delta function comes from the infinity that you would get if you took all these times and you sent them off to infinity together, keeping all the time differences fixed, right? So, in other words, there is some integral over the center of mass of all of these times, the average of all of these times, and it multiplies e to the I, the total energy, the sum of all the energies, multiplied by t bar. And this integral normally goes from minus infinity to infinity, which is where you get the delta function for E total from. That's normally where the delta function for energy conservation comes from. Now, in cosmology, it's exactly the same. There's still some contribution where all these times taken together go off to minus infinity together, except that integral, instead of being from minus infinity to infinity, is minus infinity to 0. Then dt bar, e to the I E total, t bar. And this is equal to 1 over I E total. 1 over I E, yeah, E total. Okay, so instead of delta of E total, you get 1 over E total. But what happens as you send E total to 0? As you send E total to 0, this expression is developing a pole. Where is that pole coming from? That pole is coming from that part of the time integral where all the time integrals are getting further and further and further into the infinite past. But as they get further and further into the infinite past, they know less and less and less that there is a cutoff at the boundary here at t equals 0. So what multiplies the coefficient of that pole is exactly what it would have multiplied if there was no boundary here to begin with, which is the scattering amplitude. Okay, so that's why there's this very simple relationship between the wave function and the scattering amplitude. And this is absolutely amazing, right? I mean, it has this very simple one-line physical argument. But it means this observation, look at the night sky, right? You measure these totally static measurements, you're not doing anything, you're just correlating things, spatially averaging them. If you get these functions, if you measure them sufficiently accurately so that you can do the analytic continuation where you make some of the k's positive and some of them negative, then you get an amplitude. And what amplitude? Well, you get to decide who's in and who's out because of who you decided, which energies you decided to make negative and which energies you decided to make positive when you did the continuation. Depending on which are negative and which is positive, it tells you what the in and outs are of the scattering process that you're going to get. Okay, so it's truly remarkable that a totally static measurement in the night sky has the information in it about all the collider physics dynamics that went in to the production of the perturbations that you were looking at. Okay, so let's summarize, and then. So with all this kinematics out of the way, we'll come back and talk about the geometries. Yes. This is assuming that it's conformally coupled. Yes. Although the statement that you get a clean pole is a statement about the flat space wave function. The statement that you get some kind of singularity is true universally. For any cosmology, and what you get is not the flat space amplitude, but the high energy limit of the flat space amplitude. Because this argument tells you that things are dominated as the times go off to minus infinity, that if you have, let's say, inflation, would further blue shift all of the energies as you go into the deep past. Okay, so you're not just getting the amplitude, but the high energy limit of the. But apart from that, everything else is exactly the same. As the statement of the flat space wave function is just flat out true. So there's always a pole, and the coefficient of the pole is given by the number. Okay, so we have, let's put here, we have amplitudes, wave functions, or cosmological wave functions, or cosmological or flat space wave functions. Okay, so here we have a momentum polygon. Here we have a momentum polygon. So here it's about non-overlapping chords. Here it's about non-overlapping. See, in every respect, it's slightly richer. So polygons. And yes, but so this has the sum of the k is 0 and the sum of the e's equals 0. And so the amplitude is contained inside the wave function when the sum of the e's is taken to 0. Okay. All right. So now I told you that for a long time, well, we've had evidence for interesting geometric structures that calculate autonomously the amplitudes. We've also known for a long time this connection that the amplitudes live in this codimension 1 surface inside the wave function. Okay? So this is why it has been simply inconceivable that there is no analogous story for wave functions. It just cannot be that you have all these miraculous properties of amplitudes and they just disappear when you're talking about the wave function. When you just go on this codimension 1 surface in the big space and poof, all these amazing things. It must be the other way. It must be that everything we see about amplitudes is somehow enriched in some interesting way as we go to think about the cosmological waveform. And that's what we're going to see in the next lecture. Okay, so in the next lecture, we're going to sort of quickly review the story of the isosahedron and how things work for amplitudes. And then we're going to see that to go from the isosahedron to cosmology, you literally take the isosahedron and you shave it. You take the geometry and you just do a very simple and natural thing to the geometry to shave off facets and turn the isosahedron to what we call the cosmological. Okay? And the cosmological is the object that captures all the combinatorics of non-overlapping subpolygons in the same way that the isosahedron captures the combinatorics of non-overlapping chords. Since in the title of these talks, I was asked to talk about cosmological polytopes, plural. There is an earlier version of an attempt to connect the cosmological wave function to geometries that we did not know how to make sense of for the sum of all the diagrams, but just one diagram at a time. I should have maybe emphasized this point. Actually, maybe I'll just make this point now before we break. Wave functions are more complicated than amplitudes, okay? And a lot more. So let me give some. So let's say we talk about this wave function at endpoints. The number of diagrams for the amplitude, sorry, the number of terms in the amplitudes. I mean, the same number of diagrams, but as I told you, every one diagram has a lot of terms associated with it. A single diagram, you have to sum over all the tubings of that diagram. Okay. Now, the total number of diagrams grows exponentially, grows like 4 to the n. It's the number of triangulations or the Catalan numbers that grow like 4 to the n. But the number of tubings in a given diagram grows factorially. Okay, so the cosmological wave function is a factorially complicated object, whereas this guy is factorially complicated. This is exponentially complicated. That means we're going to have a polytope that has vertices corresponding to all of these Russian dolls. So it's going to be some cool polytope with order n factorial vertices, not exponentially many things. Okay, so this guy is quite a bit more complicated than that one. Nonetheless, as we'll see, they're super duper closely related to each other. Okay, that was the point I was making before. Okay, right. But already a single diagram is complicated. And there was a story for a single diagram, any kind of diagram at all, that connected the wave function for the single graph G was the canonical form of what we call the cosmological polytope associated with G. So this was an interesting polytope that was associated with any graph. Okay. Now, I'm not going to have time to tell you about that cosmological polytope in detail, although again, I'm very happy to talk about it offline afterwards. But something else but I'm just telling you the structure of what I'm going to tell you about next when it comes to cosmology. Something else that many of you who know about associator, how many of you know about associator, know what graph associator are? Okay, fewer of you, okay. Well, there's this nice notion of a graph associator associated with any graph. And that's not the cosmological polytope. In fact, there was a little bit puzzling that there was yet another polytope associated with graphs. That was not the graph associator. And in fact, we now understand it's the graph associahedron. There is a way of associating a graph associahedron with exactly the same pictures. Okay, and it's actually related to the cosmological polytope, and it's a particular slice of this larger cosmological polytope object. So I'm not going to talk about cosmological polytopes. I will talk about these graph associahedra, but that's the relationship. So every single diagram is going to be associated with an interesting object called the graph associahedron, and the graph associahedron is related in an interesting way to the underlying cosmological polytope. So I might, again, if anyone's interested, I can define this as one of those things that has a one-line definition, but lots of interesting properties. So I won't be talking about this cosmological polytope, but it's intimately related to the graph associator. So we're going to see that every diagram, the contribution to every diagram, all the tubings of this diagram are naturally associated with these graph associator. But on top of that, all these graph associator are naturally glued together in a master object that combines all the diagrams together, which is like the associahedron. So like the associahedron combines all the diagrams together, but the vertices and facets of the associahedron are blown up in a very interesting way to tell you what you get, these sort of graph associahedron contributions you get from all the diagrams set. Okay, so those are the sort of three objects. There's the cosmological polytope associated with single graphs. There's a graph associahedron associated with single graphs in a somewhat different way. They're all glued together not just for a single graph, but all the graphs into the cosmohedra. And something that I will definitely not have time to talk about is that, remember I told you have to do some processing to this wave function. You have to mod square it and so on to get the final cosmological observable, the actual observable. So it's a very natural question to ask whether there's a geometry for the final guy, not just this intermediate object. And that also turns out to exist. And so it does not yet have a name. It will be out in a paper. So this is work in collaboration with Carolina Figueiredo and Francisco Rizal. Carolina and Francisco are going to have a separate paper out soon that defines this larger object that I want them to call the correlatron, but they will probably not call it that, which is the object which actually directly computes the correlator. Okay, so we had hints of this in our paper back in December, but they totally nailed it. It's a spectacular object. And something which is amazing about it, well, anyway, that in the story of the correlator, you see, it has everything to do with the Born rule. It has everything to do in quantum mechanics with something nice happening when you mod square a wave function. This is something that I've been desperate to see in the amplitudes world for all the times I've been working on it. Why, given the wave function, would you ever think of mod squaring it? We do all these fancy combinatorial geometric things to calculate amplitudes in the 21st century, and then we mod square because Max Born told us to do so in 1927. That's super lame. It would be great if there was an intrinsic reason, intrinsic to the combinatorics and the geometry for doing the mod squared, and there is. That's what's remarkable. Really, sort of mod squaring it really has a meaning. And anyway, that's a part of this story. So I will not have time to talk about the correlatron, but we will talk about the associahedron, graph associahedra, and the cosmohedra in the next slide. Okay, thank you.